collaborate with NASA's Jet Propulsion Lab, where I look at ways of creating new materials to be used for thrusters that are used in electric propulsion systems. What we're trying to do is have a body that's more robust mechanically, as well as better when it comes to thermal shock resistance, that's coated with boron nitride to give the biomaterial the dielectric properties that it needs. So in this way, what we're doing is creating the next generation of space materials that can be used for future launches. The other project that I'm working on has a very different application, and that's our conservation science. So we can use the same fundamental knowledge of material science processing and characterization to reproduce 18th century lusterware porcelain from Germany. So I have two projects with very different applications. One is aerospace engineering, the other is art conservation science, but I can apply my knowledge to both of them.
So my group is a new group here at Caltech, and we're building a new lab which is going to focus on thin film deposition techniques to grow a wide range of so-called quantum materials. So we're hoping that we can build new artificial crystals, which these don't exist in nature. We can do these in a controlled environment within the lab to build structures which we can manipulate and bring out novel functionalities. At some point in the future, this will have broad impacts in the field of electronics or optical devices.
I developed new algorithms to study energy conversion efficiency in energetic materials. It promotes our understanding of the fundamental physics, also facilitates the design of ultra-fast light emitters and other energetic materials.
In our group, we create an open source code for researchers around the world to simulate the electron dynamics inside solid-state materials. So I'm working on developing advanced algorithms and computational methods to simulate materials properties such as electrical conductivity. So to describe electrical conductivity, we cannot using classical methods. Then instead, we have to use quantum mechanics.
My research interest is making pearl ceramic. We're looking for a new way to allow us to have precise control over the pore structure. And one of the ways to fine-tune the pore characteristic for different applications is to use a pore forming technique called freeze casting. And that is basically if you have a solution of pre-ceramic polymers, then you freeze it, and by controlling the solidification's condition during freezing, you can get different pore size, you can get different pore morphology, and that allows you to change the structure and the property of that pore structure.
The passion for science here is really, it permeates the entire administration as well. Caltech is run by scientists. It's the faculty that come together and actually come up with the rules. I think that what's very comforting for me is that if ever we're posed with some type of challenge, I feel that as long as you can come up with a plausible scientific reason or scientific motivation as to why this should be changed or why this should be the case, people are willing to listen and people are willing to support you. And that is what leads to a healthy set of ideas being exchanged.